I think we're ready to go. So first thing we're going to do is we're going to sketch a graph of this equation. Okay? And so to sketch a graph of this equation, we need to know maximums, minimums, vertical asymptotes, x-intercepts, y-intercepts, that sort of stuff. Okay? So we are just going to start. Let's do. It really doesn't matter where you start. I'm going to do x-intercepts and y-intercepts first. Actually, I'm going to do the y-intercept. X-intercepts might be harder. Y-intercept. For y-intercepts, you just plug in 0 for your x. So you'd have 2 times 0 squared minus 9 over 0 squared minus 4. And so that would be negative 18 over negative 4. So you got a y-intercept at 9 halves, or 4.5. For the x-intercept, you're going to plug in 0 for y, so you'd have 0 equals 2 times x squared minus 9 over x squared minus 4. And the denominator really doesn't matter here, because the only way this can equal 0 is if the numerator equals 0. You can sort of think of multiplying both sides by x squared minus 4. So that gives you 0 equals 2 times x squared minus 9. Divide off that 2, so 0 equals x squared minus 9. X squared equals 9. So x equals plus or minus 3. So you've got x-intercepts at 3, 0, and negative 3, 0. Also have a y-intercept at 0, 4.5. So we know those points are on our graph. Vertical asymptotes. Where would we have vertical asymptotes for this graph? It'd be at negative 2 and 2, because if we take that denominator, x squared minus 4, and set it equal to 0, x squared equals 4, so x equals plus or minus 2. So we have vertical asymptotes at x equals 2 and x equals negative 2. What about our horizontal asymptote? Okay, for our horizontal asymptote, we're going to do the limit as x approaches infinity of 2 times x squared minus 9 over x squared minus 4. So, Cameron, when we do the limit as x approaches infinity of that, what will we get? It'll be 2. Because you'll do Bobo-Botno for that. You've got same exponents on top and bottom. So just 2 divided by 1 gives you 2 for that. Okay, so we have a horizontal asymptote at y equals 2. This is all good information that helps us graph our equation. The last thing that we want to look at is the stuff we've done most recently, and that's our increasing, decreasing, maximum, minimum, concavity stuff. So to do increasing and decreasing, we've got to look at the first derivative. So f prime of x. And it actually might be a little bit easier if we go ahead and distribute that 2. So 2x squared minus 18 over x squared minus 4. So we would have x squared minus 4 times 4x. 4x. Minus 2x squared minus 18 times 2x all over x squared minus 4 squared. And so if we distribute here, we get 4x to the third minus 16x 14x minus, we'll distribute that 2x, 4x to the third plus 36x all over x squared minus 4 squared. And so our first derivative would be the 4x squareds cancel. We'd end up with 20x over x squared minus 4 squared. And so if we think of this, we're going to have critical points at -2 and +2. Those come from here. And also at 0. But the denominator is always positive, right? Because you've got something that's squared. It can equal 0. It equals 0 at -2 and +2. But it's always positive. So it doesn't change anything. So we would have, our derivative would be negative for anything below 0, and it's going to be positive for anything above 0. Okay, so that tells us that we're all the way up to 0. F of x is increasing, and then here it would be decreasing. And then, if we're looking at our concavity, we would need the second derivative. So for second derivative, f double prime of x, we'd have x squared minus 4 squared times 20 minus 20x times 2x squared minus 4 to the first power times 2x all over x squared minus 4 to the fourth power. Okay, and what I would do here, this is sort of like a little shortcut. I could factor out x squared minus 4. It's going to cancel with one of these here. What I'm going to do is I'm just going to cancel one of these here, make that 1, and I'm going to cancel this one, and I'm going to reduce this to 3. That way I don't have to do quite so many steps. You can only do that if you can cancel it with both of your terms here. So now I could distribute, so I'll get 20x squared minus 80 minus 80x squared, is that right? Yeah, 80x squared all over x squared minus 4 to the third power, which equals negative 60x squared minus 80 over x squared minus 4 to the third. So you're going to get critical values here at -2 and +2. And if we set the top equal to 0, we would have negative 60x squared equals 80. So x squared would equal negative 4/3. And when you square root both sides of that, you get an imaginary number. So you don't get critical values for that. And if you think about this, negative 60x squared minus 80 is always negative, because x squared is going to be positive. You got negative times a or minus a negative, this is going to be negative. So this is always negative. and then x squared minus 4 to the third. If you plug in like a negative 3, then you will get a positive. It will be a negative here and a positive here. So you end up with negative, positive, negative. So that's concave down, concave up, concave down. So there are all kinds of things going on here in this graph. And so your goal is to make a good picture of that graph. So if we're graphing this, we draw in everything that we know we will have. We have y-intercept at 0, 4.5. We have x-intercepts at 3 and negative 3. We have vertical asymptotes at 2 and negative 2. We have a horizontal asymptote at positive 2. Our graph is increasing up to 0 and then decreasing. There. Oh, you're right. I did that backwards, didn't I? Let's switch that. This is decreasing and increasing. So decreasing up to 0 and then increasing after that. We're concave down from, we're concave down up to negative 2, concave up here, and then concave down. So to have this be concave down and decreasing, it's got to look like this, and you'll have a vertical asymptote here. For this middle part to be concave up, it'll look like this. You'll have those vertical asymptotes there. And we're decreasing here. Then we switch to increasing at 0. So that still follows what we found there. And then over here, we're going to look like this. So I'm not going to have you do this too often because it takes a lot of time to get that full picture. I do think it's kind of cool how you can find out so much information about a graph without actually graphing it. Now, you're probably saying, Miss Hyatt, we have this, most why don't we just type it in and see what it looks like? I agree with that too, but it gives you a lot of good reasoning about how the derivatives work together to do a problem like that. The rest of these are going to be things that we just have to answer questions from graphs and things that we're given. So this is pretty much the same chart that I put up here. If I know that the first derivative is positive, that tells me that f of x is increasing. And if I know if the first derivative is negative, that tells me decreasing. And it's really important to keep increasing and positive separate in your head because those are easy to get mixed up. Increasing means we're going up from left to right. Positive means we're above the x-axis. You could be positive and still decreasing. Okay? A second derivative, if it's positive, that tells us that our graph is concave up. And if our second derivative is negative, that tells us that our graph is concave down. Also, if our second derivative is positive, that tells us that our first derivative is increasing. And if our second derivative is negative, that tells us that our first derivative would be decreasing. And this pattern's always true. Like if we had the antiderivative of f, if we found the antiderivative of this, so went like the step above, then this would be concave up and this would be concave down. Alright, so your chain of derivatives always produce the same pattern. You don't know how to find the antiderivative yet, although it worries me that we haven't got there yet, but we're going to be okay. So this is what you got to keep in your mind and keep straight. Let's look at the first question. I know these are really small. I was copying them from the AP Classroom stuff, and it won't let me copy the words and make it bigger. So this is sort of what you're going to see. This is a calculator active problem. The first derivative is 3 natural log of 2 plus cosine 2x minus x. And the second derivative is given there, and it's really long and complicated. It wants to know on what open intervals contained in negative 2 less than x less than 2 is the graph of h both increasing and concave down. Okay? So if the graph is increasing, okay, increasing or decreasing tells us about the first derivative. So, Lily, the first derivative, what do we know about it if our graph is increasing? Positive. Tell me in a minute, okay? Alright, so this increasing tells us that the first derivative is positive. And then concave down, what does that tell us? Concavity, Justice, which derivative do we look at for concavity? Second derivative. And if we're concave down, what does that tell us about our second derivative? Not decreasing, negative. Okay? To make this a little bit quicker, if the second derivative is negative, what does that tell you about the first derivative? It is decreasing. Okay? So if we could find where the first derivative is positive and decreasing, those are the places where the function is increasing and concave down. You can, because they give you the first and second derivative here, you can look at them separately and then put that information together. But if you look only at the first derivative, it's going to save you a little bit of time here. So if you graph this, we are going to have 3 natural log of 2 plus cosine 2x minus x. Okay, I think that looks right. And so we're only looking from negative 2 to 2, so I'm going to go to my window first and make this go from negative 2 to 2. And then I'm going to graph. And so I'm looking for where this first derivative is positive but decreasing. So the first derivative is positive all the way up to this point right here, which just looking at this, I'm going to guess is probably 1.6, but I could actually find it, I guess. But I need to be positive, but also decreasing. So this first little section right here is positive, but decreasing. Right? So it'd be from negative 2 up to this point, which is probably that negative 1.486. And then I also decrease from this, I'm positive, but decreasing from this point up to here. So that is probably negative 2.50. I probably need to figure out what that value exactly is so I know which one of these is correct. So I need to find this 0 right here. So 0. And when we find that, I think it's going to be the 1.08. Yeah, 1.085. So A would be the correct answer there. You could look at that second derivative, but it's just a little bit faster if you look at that first derivative. Let me think here for a second. We are getting so far behind. What I want you to do tonight, we do have an assignment that's going to be on the My AP, but without going through these problems, I'm not sure we need to look at it yet. So tonight, I want you to try to answer the rest of the questions on the notes. Okay? You have all the information you need to be able to answer those. We just haven't done a lot of problems like it yet. So try to answer the rest of those for homework, and then tomorrow we'll look at that stuff on the My AP.